Welcome friends to the 16th module of AI. In this particular module, we will be looking at forward and backward state space planning. Now, the word planning is mentioned a few times in the earlier modules, and in this particular module, we will be discussing about what do we mean by planning and what are forward and backward state space planning, or sometimes called forward planning and sometimes called backward planning. Now, an interesting observation probably has revealed this thing to you. We have talked about many problems so far, but then not all problems are similar. For example, if I start proving a theorem and in the middle of it I find that I'm traveling a wrong path, I may start all over again, forgetting about whatever I have done so far. Now, if I am editing a Word document and done something, after a while I believe that, oh, whatever I am doing is not correct, I had to do it in some other way. Can I start all over again? I cannot. I have to undo what I have done, but I can undo. Once I undo that, I reach to a point where I want some difference, I can go ahead and do it. I'm playing chess, I have made some mistake in the second move and now I'm on the 15th move. I realize that I have made some mistake in the second move. Can I go back and do? Can I ignore? Neither can I ignore, nor can I go back. So, there are three different types of problems. One problem is where you are exploring the search space, at the middle of it you just forget about where you were and start all over again, absolutely fine. In case number 2, you can't just do that, but still you can come back, you can carefully undo the steps that you have taken and start from the place from where you believe that the error has occurred. In case number 3, you don't have either of the option. You will have to do whatever you do best from that particular place. You can't go back, you can't undo. So, these three type of problems, in many cases, obviously you can see that the problem number 3 is hardest. Now, is it possible for you to convert that hard problem into a little less hard problem type 3 into problem 2? The trick is called planning. So, you can plan accordingly. I talked about a case where you are planning your travel or you are actually traveling. When you are actually traveling, you can't go back and restart, okay, that I have already mentioned. So, actual traveling is the type 3 problem. You can't just do it, in fact. Sometimes it is type 2, you can go back and then retake, but that additional burden that you will have to anyway take. So, if you start planning, in case of chess, the great thing is to plan, see what you will play, what the opponent is going to respond and what will be your response and so on and so forth. Based on that, you can decide your move now. So, planning helps you improve this thing. Anyway, planning is also very important for AI programs. Planning is important for everything, but planning is very useful for planning a solution, because when you plan a solution well in advance, especially for problems like problem type 3, it will help you finding out the best path, because you will not be in a position to come back and choose a better path at the later stage. Before we start planning, we have to have a set of objectives. Now, it's very important because the plan always is based on the set of objectives that you choose. Let us take a very simple example of finding a route from one city to the other. Now, if your objective is to minimize cost, okay, you may choose, you may just pick up cycle, because that's the best option. But that might take 2 hours to reach to that city, but that's just fine. It's cost effective, the best cost effective solution. If you prefer the user convenience as your objective, you may prefer a luxury car to travel. But somebody else would like to look at cost as well as the luxury, probably would prefer a two-wheeler. So, given a different set of objective, the planning is going to change. Not only that, in this case also, there may be multiple paths from one city to the other. One is a very short path, but very crowded. So, if you want to travel by car, that road is not very good. You may prefer a road which is longer, but with less traffic. So, your planning is going to change based on your objective. So, this objective is very important. So, what are objectives? In fact, 2 things you need for the planning. What we want to do is based on our objectives, and second, obviously, how we are going to do that, the outcome. And what is the outcome? Usually the outcome is sequence of moves, move 1, move 2, move 3, move 4. And if you look at the previous module, they are called actions. The agent take actions. Okay, basically action is an implementation of a rule, and there is some difference also. Let me talk about that difference right now. When I say that a chess, a piece has moved 2 rows in advance to 2 rows, a piece advanced to 2 rows. That is the statement and the rule. Okay, so when the rule is applied, the matrix, the program changes, but actual movement must take place. So, agent basically is doing that. It moves that piece forward. So action actually applies the rule. So is the implementation of the rule. How the rule is implemented in real world is described by action. So when you want to apply an action, it's very similar. Remember, the rule and action are quite similar. Action is just implementation of it. If you want to apply a rule or apply an action in a given state, there are two things needed. The first thing is the prerequisite. If I want to move that piece further, you know that if I want to move that piece 2 rows ahead, both rows must not contain any other piece. So that is the prerequisite. If the prerequisite does not hold, I cannot generate this rule. So this action is not possible if the cell on which I want to move is occupied. Okay, so that I cannot do. So the prerequisite must match, okay, for the actions to apply. In fact, the other important thing, there may be multiple actions available to us. Obviously, the first requirement is prerequisite with the action must be applicable in a given state. The second thing is the action may be acceptable, but will that action yield a goal, or will it move my state nearer to the goal state? If it does, then it is better, it is more acceptable. So this is the other thing which we are interested in learning about. So sometimes when you have multiple agents, you will need to choose an action which moves us nearer to the goal state, and such actions are known as relevant actions. And whenever there is a sequence of actions A1, A2, A3, A4, A5, then A1, when A1 applies, it generates the prerequisite for A2. When A2 is applied, A2 generates prerequisite for A3, and so on. Okay, so this is the other requirement. Well, there is an example. For example, an agent which is capable to detect an intrusion. There is a state which says that there is a possibility of denial of service attack. Now you will have to move on from this state, and one of the objective of intrusion detection agent is to, whenever there is a possibility, the objective is to confirm. So it should go to a state called confirm this thing. Okay, so it has to move. The other objective is to, obviously the other state is to communicate to other IDS agents running elsewhere in the network, and the third one is to take preventive action. So these three things are to be done. So what does it do? It generates the attack sequence, attack response sequence, I would say. Check for an attack, confirm the attack, and then take the preventive action. So these three actions will happen. Now you can see that these three actions will happen only in this sequence. You cannot just take a preventive action and then do something. You will have to confirm that attack before. So without which you cannot work. Similar case is described in handout using the possibility of threat of fork in chess. An interesting issue here is that not only we are planning, but attacker also is planning. So when we are doing something, the attacker also is doing something. Okay, so what we have to do is to make sure that our plan is such that even if the attacker plans something which thwarts our plan, we'll have to outthink the opponent, and that is quite an interesting job. So planning is not always that straightforward. When there is an opponent involved, like chess, we have already seen some issues related to that. Okay, when the opponent outthinks us, we're going to lose. Okay, so that is critical here. There is a sample list of objectives which are provided on the next slide, which talks about restrict attackers at access to minimum, disallow any system disruption, and so on and so forth. Now the idea is that when I am planning, these objectives are to be met, but not in all cases all objectives are possible to be met. You will have to compromise actually. Sometimes some objectives are met, sometimes some objectives are not met. There are two alternatives. One alternative 90% of objectives are met, in the other case 80% objectives are met. That is quite possible. So objectives and actions, when you try to link, okay, our actions must take, the action must align with our objectives. For example, when we learn that malicious user's IP address, we know that this is malicious users, we can block him. Now you can't just block an IP address without knowing it. So that sequence is to be followed. The action can only be taken if there is a prerequisite. The action is only possible if some action is taken to generate that prerequisite. For example, I want to block an attacker's IP address, I must execute some action which get me that IP address. So that actions are to be listed that way. Now, I like when we start from the start state and when we reach to the goal state, we continuously make sure that the objectives are addressed. Then there are two different type of constraints. I call them soft and hard constraints, and I take an analogy to explain what these things are, and taken it from an academics domain. There is a timetable which is being prepared. Now, one constraint says that a teacher cannot take two classes at the same point of time. Now, this is a hard constraint. You cannot violate even if you wish to. You cannot violate this. But the other constraint, which is called soft constraint, The teacher cannot take 2 consecutive classes. Now that is a good thing to have, that if a teacher has to take 2 consecutive classes, the delivery will not be to the same level. So you should try to avoid, but it is not that teacher cannot do. So this is called a soft constraint, which you can violate once in a while. So the objectives are also of that type. Okay, user convenience. For example, user convenience is one objective that I have to meet. So user should not find the network being slow or the server is not accessible and all that. But when there is a serious attack happening on network, it is better, you can say that the user convenience take a backseat. You just pick up whatever steps that you need to for thwarting that attack. Let the user be a little dissatisfied with the service, absolutely fine. So the objective takes a backseat. So that has to be there. So this is additional issue. What you're supposed to do is to find out hard and soft constraints and follow a path which help you manage both types of constraints. Okay, and based on that you decide what your performance is. And there are many types of planning, simple and detailed planning. So simple planning, you don't do much, you just narrate and it is done faster. But the issue is that detailing may be different and might create an issue. Detailed planning is better because you don't need to worry while you are implementing, but then it takes more time. Okay, but then there are other issues. For example, one is whether the world is predictable. So you say that I'll take this, where the world will be like this, and then I take a further step. Like playing card, you say that I play this card, and then because others will play this, I'll play one more card. Now that is not in your hand. The world is not predictable. In case of self-driving car, world is far more predictable. When you know that when I apply brake, the speed of the vehicle will reduce. When I apply accelerator, the speed of the vehicle will increase. So world is predictable, and I can predict the outcome of my action in most of the cases. So world is definitely, but then world, if you pick up an 8 puzzle case, world is extremely predictable. I can provide sequence of actions and will clearly tell me whether I'll be able to get the answer or not. Driving car is not all that predictable, and playing card is almost unpredictable compared to that. The third one, the next one, world is changing while it is being deliberated. Now you have the situation, now you're thinking about taking a next step. By the time the world changes or not, in case of chess, you have the chess board, the opponent has played his move, and you will have to play your own move. But before that, you may think for a while, 2 minutes, 5 minutes, 10 minutes, the world is not going to change. The world is going to remain the same. Unlike that, in a self-driving car, the world might change, and it is changing actually. If the self-driving car takes 5 seconds to take a decision, it wants to take a right turn, and it looks at everything and start the right indicator and everything. It looks at the right mirror and all that, and it's working on it, and 5 seconds elapsed in that. And can it do it again? Like it has to, in fact, look at the right mirror just before it plunges. It changes the direction. Why? Because the world is changing, and last 5 seconds there is probability of some other vehicle come in the view and come in such a way that if it takes a right turn, now it might meet with an accident. So the world is changing. So that's the other issue. The fourth one is whether the world is completely visible or not. Sometimes the world is pretty visible. In case of chess, the world is completely visible. The self-driving car, if there is no weather related issue, is again quite visible. In case of cards, no, the world is not visible. You don't really know the cards others have. You just can assume, you can just predict and work, okay, just guess and work. So for each one of them, you require different types of planning. And why we are using, again, let me tell you why we are talking about agent-based issues search. Agent-based search is the same as the other search that we have seen, but it is more explicit and detailed. Why? Because when I say that I take a right turn in a graph based that thing, I said right turn and done. But what is right turn? In case of agent based, it says that the right turn, there is an action, there is something which is to be done for taking a right turn. Okay, so that detailed procedure is specified. Not only that, there is something which implements that also. Okay, for example, it says that it will move the steering wheel in a typical clockwise fashion to do it. So that algorithm, that process is also provided. So it basically contains a program which implements that action, that rule, okay, so which I have already told you that action implements the rule. So here it is the example. We become more explicit. And that planning, when we do plan, there are 2 different ways to plan. One is use planning based on the previous experience that I have. For example, I'll have to plan a conference, and I have 20, 30 conferences planned already, and what I have learned over the years, I may use to organize the next conference that I am going to organize. It is quite possible that next time I have to organize an international conference. I have never done that, but then my own experience, partial experience of organizing national conference may help me. I may be given a job which I have never done in past, and I will have to give a fresh look and do it all over again. Okay, so these two different cases. First one is called case based reasoning. You just, whenever you have a problem, the agent has a problem to do. Okay, that case based reasoning is the other one. The case based reasoning is a very simple way of reasoning. Whenever you come across a problem, you just look at in your database. If there is a problem which looks similar, find out the solution that we have taken and apply there. For example, I am an intrusion detection agent. What I will do is, when I encounter a new attack, I just try to compare this attack with the attacks that I have already seen in past. If I find a similar attack, I will find out what did I do to solve that problem, okay, and then I will follow that process. Okay, so but then if a fresh case, I will have to follow a different approach. Usually something that I have already done. I apply heuristic, I generate the search space, and I move across the search space. Hopefully I will reach to a goal state. Okay, case based planning sometimes is known as memory based planning, because a job is done in memory. Okay, the next thing that we are going to look at is called forward planning or forward state space planning. Now what you do is, you generate the percept sequence which lead to the final state, or the actions or sequence of actions to lead to a final state. So basically the output of any planning is action sequence, forward or backward. Forward, you start from action number 1, 2, 3, 4, 5 in a way that you start from start state and reach to a goal state. In a backward reasoning, you start from action an minus 1 and so on, such that you start from a final state to just state before and so on till the start state. Anyway, that's just fine, but then the actions, what will be the order of the action? In one case, both the actions, action A1 must appear, one must execute before action A2, then it is called strict ordering. For example, pressing a clutch and changing the gear. Now A1 must happen before A2. Okay, if you don't do that, it will not happen. So that's strict ordering. But starting an AC and increasing the accelerator value are two parallel things. They are not related to each other. I can order them in any way. So there is no order, unorder kind of. Okay, but then there is a partial ordering. For example, I can start the AC or change the gear, but then that only happens after starting the car, without which I cannot do it. So that's called partial ordering. There is an example I purposefully chosen here, shown on the PPT, which indicates a case where backward reasoning is better or backward state space planning is better. Now you can see that initial state, and there are multiple states you can generate from initial state, but from the final state, you just look at that, you will realize that it's pretty fast for anybody to convert that final state into the 4 different components of initial state, because the problem is I have designed that way. I have contrived this example to showcase the usefulness of backward reasoning. In this case, the backward reasoning is quite useful. So some possible moves are shown here. So if you begin with the start state, what you can do is, there are two things. One, pick up a block on the top and put it on the table, or you can put it on some other stack. Okay, there are 5 stacks in the beginning. So there are plenty of options available. So the first row talks about putting G on the table, then D on the table, then C on the table. So the topmost item we are putting on the table. So that's one. Second one, picking up G and putting it on top of C. Next one, D, picking up D and putting it on top of somewhere. Okay, the next one, C, and putting it top of somewhere. So you can see that there are plenty of options available. If you move backward, this is not going to happen. Move backward, only possible state is putting A back on table, and this is the only possible option, and that's why it is better, because you only have one option. Okay, when there is one option, you don't need to choose, and it becomes fast, and that sometimes is called branching factor. Branching factor in the forward direction is very high, branching factor in the backward direction is very small. Sometimes backward planning is also known as goal directed reasoning, but then you might take some steps. It's very important for you to also see whether that is in the right direction. I said I use the word relevant. So sometimes you will have to also see whether the move is relevant or not. And this is not heuristic. Please understand this. I am not talking about heuristic right now. Assume that there are some components in the start state, there are some components in the goal state. Now, when you move, there are some components which are there in start state, but not in goal state. There are some components in goal state which are not there in the start state. So, whenever you apply an action, suppose if it adds a component which is there in the goal state and not in the start state, it is good. It deletes a component which is there in the start state and not in the final state, then also it is good. Now, these two important things indicate that this action will convert the current state into a state which is nearer to goal state than the start state and moving it from start state to goal state. Now, that is important here. But then many a times, that is one thing, the relevance of a state, that is one thing which I wanted to talk about. The other one is that the planning is unaware about interdependency of sub components, and this whatever I have discussed about is not very important, not very useful. An interesting example is shown in a figure. B is resting on table, A is resting on table, C is resting on top of D, D is resting on table. Now, what you want to have is A is resting on B, B is resting on C, and then D is resting on table. Now, what I want to achieve is on table C, on table D, on BA, on AB. Now, this is what I want to have from this. Now, out of this, I say on AB is my first component. Okay. If I try to achieve that using this, the problem is, and you can see that if I place A on top of B, it is nearer to the goal state, but it is not goal state. In fact, it is, I have to break it apart again. Now, this is very similar to something that we have seen while we discussed about local and global heuristic functions. Though I am going towards goal state, this is not the right way of doing it. So, these are interconnecting goals. So, what I am talking about, the relevance and component and all that, is only important or useful if the goals are not interdependent, the sub goals are not interdependent. If they are interdependent, I may solve on AB, which makes the start state nearer to the goal state. Well, I will not reach to goal state if I do that. Okay. The next important thing is to say, in a given case, which one should I use? Should I use a forward reasoning or backward reasoning? There are many ways to say. We have already talked about the branching factor. The branching factor from start state to end state is more than we should not drag from goal state. But then there are other alternatives. For example, other alternative ways to judge this. For example, if I tell you to go to a place which is unknown to you, from a place which is known, your home, or the option, you can start from that unknown place. Most of us will prefer to start from that unknown place, because from that unknown place you travel in any direction, you reach to a place which is known to you, you can always connect that to your home. So, you can always come back. What does it mean? If you start from your home state and would like to complete, you will have to be there at the place where you want to be, because in unknown place you don't know from where you will reach there. So, without you reaching there, you don't really know whether you have reached to a goal state. Unlike that, number of options when you start with an unknown place is plenty, and all of them are start state for you. For example, if you start from the goal state and you reach to 10, 15, 20 places from where you can reach your home, there are plenty of options available. Those 15 options are possible. So, you can reach to any one of them and you will reach there. So, when such an options and more number of options are available, it is better. Second issue is what type of problem is being solved. For example, if you are looking at a big data inquiry that is coming in, look at the amount of posts and let me know whether my product is being sold or not, whatever. So, what I am actually do is to understand what the query is and process backward, because I start from query, I receive a query, I will have to process back. I can't start from the beginning. I don't really know. Or if I have a game playing program like chess, now I cannot start from the final state. I don't know what the final state is. There is no way for me to know, not only for a conventional state chess program, but you probably have seen many puzzles coming in everyday newspapers, some chess puzzles. Even for those cases, there is a single start state, but there are multiple possible end states. So, it is always better to start from the initial state or whatever state that you are given. So, point is, in this case, forward reasoning is better. The other one, if explanation facility is required, if the agent is supposed to explain the reasoning, for example, if you take a automated taxi and it says that 500 rupees, you may ask why 500 rupees, it has to go back and explain why 500 rupees. And when somebody says that normally I pay only 400 and you are asking 500, why it is so? It must process back and find out the reasoning for it. So, whenever explanation facility is required, the agent will have to look at the planning process from the goal. Okay, so the goal directed reasoning or the backward reasoning is very, very important in this case. The other case is how the solution will be implemented. For example, if I am using Prolog to implement the solution, Prolog is by default is a backward chaining mechanism. So usually you provide your goal, whenever you run up, provide your goal and will find out the solution. Okay, it will always travel in a backward direction. So if you are using a language like Prolog, the best option is to move back. If you are using conventional languages, if you use Java, C++, Python and all that, the best way to start from the beginning. It does not mean that you cannot start backwards, but natural flow of such programming languages in the forward direction. So, it is better if you do it that way. Okay. So, that is the point. With that, we will come to an end of this discussion, forward versus backward reasoning, which we have seen in the end. There are a lot of things that we have discussed. We looked at the planning process, we looked at the components of planning, we looked at what is good planning, we looked at agent based planning, the problems, the world, the environment related issues and so on and so forth. And at the end we have compared forward and backward reasoning processes and advantages and disadvantages. Looking at all this, we are now ready for talking about the planning process which happens in the real sales programs. Okay, so we will be talking about that in the next module. With that, we will conclude. Thank you.